we have. So good morning, everyone. Happy to see every one of you here today. Please post your questions. Don't send me a direct message. Please post on everyone so that everyone can see your questions. Even sometime in the flow of technical thing, I'm not able to share or answer your question. Other people in the chat, other mentors will be able to answer that questions for you, right? So please use the chat sections to answer also, right? Let me start with this. Okay, so today agenda is we will understand some battery fundamental chemistries. In today's session, we'll understand different form factors. In today's session, we'll understand what different impacts happen of different chemistries in the cost, weight, life perspective, performance impact perspective. What are the different cell selection criterias which we have in the market? What are segment specific needs? We'll cover that also in detail. We start with this only, so not necessarily in the order. We will also simulate the impact of different cell we select for as a use case on a vehicle performance. And we'll also see what are the different growth trends which are available, how which industry is going towards what area, right? So that is something we'll also do it. Okay. Is it clear to all of you? Okay. Then we'll also go through overview of Techlanz, what we are doing, and right. Great. Let's start with this, the first part of it, right? So who is speaker today? I'm speaker today with you. No one else is there with me today. Uh, so I'm co-founder of Techlanz. I have around 10 years plus experience in the EV industry. I'm ITD alumni. I work with Mahindra and Mahindra, Simple. I was co-founder and CTO of Vito Motors also. After that, we started with Techlanz. So me and Lokesh are the co-founder of Techlanz, and we are around 20 plus plus employee team over here in Bangalore. We are based out of Bangalore. We do multiple things. We'll talk about at the end what we do. Okay, so let's understand how the target setting happens, right? How the vehicle development process happens. Let's go slow over here. Understand from the basic physics perspective, from the concept stage. When you decide that what product you want, you decide what should be the top speed of acceleration, right? You decide what is the gradient requirement of my vehicle, what's my payload requirement of the vehicle, correct? You also decide what is the range requirement of my vehicle, what's my battery life requirement, what's the warranty I should offer, and most importantly, what is the cost of the vehicle which I'm making, because always the cost is a target for you, right? After that, what you do is you derive engineering specs out of those elements, and you decide, okay, what should be the motor power to achieve that top speed or acceleration, right? What should the motor torque? What should my battery capacity to achieve the range, what the target is? What should my system voltage, and what's my weight of the battery pack or any vehicle? Right? These are the things which you derive out of your project targets. Based on that, you derived the battery level specs as well. Like what should be the current rating, AC/DC, what should be the C rates, right? What should be the DOD, what should be the cell type, what's the series parallel combination. So this is how you derive your vehicle level to system level specs. You start with project level targets. You define my engineering specs on the vehicle. Then you decide what's my system level targets. Okay. The requirements for any vehicle is different. So you cannot have a single level of requirement for all of your vehicle needs, right? For two-wheeler, the requirements are different. For three-wheeler, requirements are different. For four-wheeler, requirements are different. I've just taken a use case of over here to show you typically whatever the Indian market, this is in text of Indian market right now. Like this specs are similar to your Ather. This is similar to your Piaggio EV, and this is similar to your Nexon EV. I've just taken some reference so that you can connect to the subject and understand in much more detail. Okay. So if you see a typical range requirement of a two-wheeler is around 80 kilometers, three-wheeler some around 80 to 120 kilometers, four-wheelers some around what we get in the market is around 450 kilometers, right? This is a base level of target what we have. Based on that, you perform system sizing simulations. You understand that, okay, what's my battery capacity required for this range for a given weight condition, right? And for different targets. Similarly, for three-wheeler, for this much range, for this much payload capacity, What's my battery capacity requirement? Simple for four-wheel also, you derive these value based on simulation. What's my battery capacity requirement for different drive cycles or RWB conditions? Okay. You have this target of like for suppose for two-wheeler, you want fast vehicle 3.9 seconds, 0 to 40. For three-wheelers, the acceleration or performance does not matter much because they're still okay with lower acceleration because these are not performance vehicle, right? These are load carrier vehicles or passenger vehicles are generating revenue for the people who drive the vehicle. For them, revenue makes most important thing, right? So performance is okay, slightly can be compromised. Four-wheeler performance matter a lot. People are who are car enthusiasts, they know acceleration matters them to the most, right? So it's very important for them. Similarly, for speed, if you see decent amount of speed is required for two-wheeler, being in safe range, 80 to 100 kilometer people are offering. Three-wheeler again, decent amount of speed, not very high speed, so that you can deliver the goods at time, but not very fast speed because it will impact your battery capacity. Then for the four-wheeler, you want the vehicle to be very fast, right? You want the vehicle to be extremely fast so you can reach your destination on the highways very fast, right? From the battery life perspective, there are government norms also which calls for 3 years warranty. Most of the OEMs are offering 3 years warranty as of now, be it Ather, be it Ola, be it Simple. Recently, be it TVS, be it Hero. Recently, Ola announced 8-year warranty also with some premium on top of it, right? Which is also possible. Three-wheeler also, similar kind of warranty is available, right? People design the vehicle for 3 years warranty. But for four-wheelers, the warranty are very high, right? It should be around 8 years, 10 years, 12 years, 15 years. Sometimes people call it a million mile warranty. Tesla started with that as well, right? So objective of four-wheeler, because the cost of the vehicle is very high and the cost of the battery is also very high, people don't want to change very frequently. And the convenience is what matters the most in four-wheeler industry, right? Let's talk about the car target cost. Just tentative target cost, not very exact target cost numbers over here. Okay. So for a two-wheeler, the target cost could be around 45,000 rupees, less than that, obviously. Maximum cap for three-wheeler could be around 1.2 lakhs. Again, there's a max value. Similarly, for four-wheeler, for this battery capacity, so this is based on battery capacity. Okay, so this is some factor which has been considered, and this is for four-wheeler, not for any this one. So a specific capacity correspondingly, what is my cost targets? Then you have a dimensions also of the packaging, so you have to meet those packaging requirement as well. Very strict in case of two-wheeler because you don't have much space, right? So you have very small volume where you can package your battery. Three-wheeler, generally, this dimension is much more bigger, much more flexible, right? Especially in the three-wheeler cargo space, because under the hood, under the load body, you have good amount of space where you can put your battery pack, right? So people leverage that very well, and people don't bother about the weight of the battery also, right? Because at the end, what they want is the range, and they don't have to get the performance because at the end, the weight impacts the performance the most. Range also, but performance the most. So you're not bothered that much about the performance. So you can leverage that area which is available with you in the three-wheeler load carrier, which you can use for this. Okay. For similarly for four-wheeler, again there is a packaging constraint. You have flat underbody, you have to have maximum cabin volume for the comfort of the occupants, so that again you get limited area where you can package your battery, right? Something very very important perspective. Charging time, people want charging time everywhere less, be it the three-wheeler, but be it the two-wheeler, be it the four-wheeler. But four-wheeler people who buy the four-wheeler, they want the convenience, they want very fast charge, right? They want the vehicle to be fully charged in half an hour or 1 hour maximum. That's a requirement because the fast charging network is available in the country. People, while traveling on the highways, they want to stop maximum for 30 minutes or 1 hour on the highway while they are on a long trip. They want their vehicle to be fully charged and good to go, right? From weight perspective, this is typical weight of a two-wheeler. This is typical weight of a three-wheeler for EVs, and this is typical weight of a four-wheeler EV. Now, since I have worked personally on all the three areas, be it two-wheeler, be it three-wheeler, be it four-wheeler, I can tell you very confidently, this is the exact scenario which happens, right? Let me go in much more detail. What is a segment specific need? Now, it depends which cell you choose will depends hugely on these areas, right? So let's go segment specific need point of view. Okay. Let's divide our requirements from segment perspective to different areas, right? Which are my performance of the vehicle. Second thing, my battery size means volume, right? Third thing is battery life, initial cost. Then we have total cost of ownership. Then we have safety. Then we have charging time. Do you think any other criteria is there from the customer point of view or any engineering point of view? Put on the chat box. Let me see what your thought process are. Let me read those chats also. Right? Do you think any other criteria which decides while deciding these batteries? Do you think any other criteria which I missed out? Please go ahead and post your answers in the chat. Then I'll show you the how this chart changes from segment to segment. No one? No other criteria you can think of? Okay, no worries. But do you agree with this? But do you agree with these criteria? Yes or no? Right? Do you agree with these are all the criteria by which you will decide the what battery you should be choosing or what cell you should be choosing? Right, for your battery. So this is your basically when you're buying a vehicle, right? When you're buying a vehicle, you see all these areas. What's my charging time? Is my vehicle is safe or not safe? What's my initial cost of the vehicle? What's my performance of the vehicle? What's my total cost of ownership? Do you agree with all these areas? And what's my life of the battery? How long the battery will last? Yes, no on the chat box, please. I want to make it very interactive. This one. So replacement cost comes under your TCO, right? Total cost of ownership, right? Great, good to go. Okay, let's see how this changes from segment to segment. Okay, so if you see this from the two-wheeler perspective, what matters the most is the initial cost of the vehicle and my battery size, the battery volume. Okay, other aspect also matter, performance also matters. It's not like that performance does not matter, safety also matters. So 4 out of 5, right? But initial cost and battery size the matter the most because you have very less space under your floorboard or under your vehicle so that you can package because the vehicle itself is very small, right? So you cannot have very big area to package your complete battery pack, right? So this becomes very important when you're buying your vehicle, right? Or you're making your battery for your vehicle, right? And the initial cost of it because if you see two-wheeler is cost sensitive segment, extremely initial cost sensitive segment. People want to buy the vehicle for mobility, especially the scooter segment, not the bike segment, so that they can actually buy at lesser cost and can be used for their mobility perspective. India has 70% rural area, right, where the mostly two-wheelers are being sold also. So that becomes very important from that perspective. I don't know whether you know this fact. India is 70% rural area, only 30% is urban, right? From that perspective, and the biggest mobility area is your two-wheeler. Okay. Please don't scribble on my screen. People will not be able to see anything then. Okay. From the three-wheeler perspective, the total cost of ownership matters the most. If you ask to any auto driver or load carrier driver, for them or the fleet owner for that perspective, what matters the most for them is the total cost of ownership. Okay, the most important aspect, right? Which includes the replacement cost, which includes the charging cost, right? Remember this. And charging time also matter. So whatever the fleet owner, if you have seen most of the Flipkart, Big Basket, they have started using your three-wheeler, electric three-wheeler for their fleet operations. For them, there is batches, shifts runs, right? So from one shift to another shift, they have to charge the vehicle. So the fast charging becomes very important for them. That's the reason if you see the Altigreen, Exponent, they started putting the fast charging 15-minute fast charging, Log9. They started putting this fast charging system on three-wheelers, right? Are you aware of this? Yes or no? Right? All these Log9, Exponent, Altigreen, they have started putting fast charging on the three-wheeler category. That is not available for two-wheelers not available for four-wheeler as well, right? It's not being utilized that way. The way it's being utilized and implemented on three-wheelers. Are you aware of this? Yes, no? Did you learn something new, or this you already know? Right? So
Hi, Vishal. I'm so sorry to interrupt. Can you repeat that once again?
yeah, okay. So what I was saying that for the three-wheeler perspective, the charging time becomes very, very important. From the fleet owner perspective, for suppose I'm a Flipkart, right? I have around 100 vehicles operating. And generally what I do, I have to do deliveries of my goods, right? For that perspective, I run my shift. I have morning shift, I have afternoon shift, I have evening shift. Now from each shift, if I'm covering around 70 to 80 kilometer or 40 to 50 kilometer, I have to recharge my battery again, right? Electric vehicle. Now I have a shift break only of 30 minutes for suppose. In that 30 minutes, I want to charge my vehicle again so that my next people, the shift is there, they can again take back the vehicle and start delivering the goods. So charging time for three-wheelers become very, very important, right? More than two-wheelers. We people think that two-wheeler is important, but three-wheeler is much more prominent than that because the fleet owner profitability depends on that. A standing vehicle for a fleet owner is a loss, right? They want their vehicle to be 100% utilized all the time, right?
True,
Correct?
true, true, true.
Time is also required, TCU is also required, obviously. Definitely battery size, as already mentioned, least bothered about battery size. That's why reason the LTO battery pack, if you don't know, the Log9 builds LTO battery pack that goes in your three-wheelers and they take huge amount of space in those three-wheelers, right? Because they're not bothered about the space, because they're not bothered about the performance. What matters to them? TCO. What matters to them? Charging time. What matters to them? Profitability, which is generated by these three-wheeler vehicles, right? Safety is not low score. Okay, because what happens? People try to build safe vehicle for three-wheeler also. LTO is lithium titanium oxide. This is a battery chemistry for anode. Okay. Okay, Devendra is saying I can relate to the morning session because today morning we have battery fundamental session. First class was battery fundamental, battery whatever the battery BMS bootcamp. We went to in detail of your uh, every chemistry, every cathode chemistry, every anode chemistry. Great, Devendra. You can correlate with the session in the morning. Okay, right. So this becomes important. Safety perspective, it's not like people want to make less safer battery for three-wheelers. The consideration, the amount of effort goes in making these three-wheeler weight battery safe is much more lesser as compared to three-wheeler and four, as compared to two-wheeler and four-wheeler. It's just a comparative scale, right? So it still is three. It's not zero, right? If you see, it's three on the scale of 0 to 5, right, Amrita? Now consider the four-wheeler, very different story altogether, right? If you see the four-wheeler, people are less bothered about TCO, to be very honest. They are less bothered about initial, they are bothered, but as compared to three-wheeler and two-wheeler, they are less bothered about it. What they're most bothered about is their performance, right? What they're most bothered about is their charging time. What they most bothered about their safety. What they most bothered about the life of my battery. How next time when I have to change my battery pack. Do you agree with this, all of you? Most for the four-wheeler buyer, what matters for them is a convenience, right? I want my vehicle to be charged within 10-15 minutes. I'm going a long trip. I'm going to Leh Ladakh from Chennai, right? On the trip, I want to charge my vehicle 15 minutes. I want the vehicle to be 100% safe. I cannot afford my vehicle to burn that way. Not all, neither of the two-wheeler, three-wheeler, or four-wheeler can afford that. But the four-wheeler people have the highest consideration and the highest safety standards are kept in place for four-wheelers only. Okay. If you see from battery testing perspective, the norms which governs the battery safety in four-wheeler are much more stringent than two-wheeler and three-wheeler. The people who are from industry, they know this fact. Okay. Similarly, performance-wise, you cannot afford to have bad performance. That's of your four-wheeler vehicle. Correct. All of you, are you aligned with this? This is something you find this is insightful? Put yes or no in the chat box first. See, I have to make it interactive session. I also need to get some energy from you people. Because I'm already very much tired since morning. I'm just training. To be very honest, we are training in the morning. Also 9 o'clock we started. Okay, this is my second session of the day. Okay, I need some energy from all of you. Yeah, great, great. So let's see what are the different form factors we have. Okay, we have cylindrical form factors, we have pouch form factor, we have prismatic form factor, and I think I missed that. This is slightly swapped. I understand that this is pouch and this is. Let me correct it right away. Why not? Oh, 1 second. Let me quickly correct this. Then you will say that okay, Vishal was not training right. So let me share my screen again. Right. So this is my pouch cell and this is my prismatic cell. You can see all of you can see my screen, right?
Yes, sure.
Now, if you see that cylindrical cell and the prismatic cell as well as pouch cell, they comes in different shapes and size, right? The most important or most common abbreviation for the cylindrical cell you might have seen 18650, 2170, 4680, which was popularized by Tesla, none other than Tesla, who became the pioneer of the electric vehicle earlier. But once the Chinese people, BYD has taken care, BYD is the pioneer currently in the market. So I'll go in depth later on. But this is a form factor, and 18 becomes your cell diameter, and 65 becomes your cell height. Similarly, 21 becomes my diameter, 70 becomes my cell height. For 4680, 46 become my cell diameter, and 80 becomes my cell height. This is a abbreviation how the cylindrical cells are defined. Prismatic cells are defined in LBH, very straightforward, length, width, and height, right? Okay. So I'm happy that chat people are chatting each other and answering the question, right? Let's see the comparison of different cells, right? So what happened at different cell level? If you compare a specific energy, you will find that the pouch cell has a highest specific energy because there is no enclosure, right? Generally, you will see the enclosure of pouch cell is very minimal, whereas in prismatic you have very hard case of aluminum or steel. In case of cylindrical cells also you have hard enclosure in cylindrical format, right? So if you see that from a specific energy perspective, your pouch cell has the highest energy density, right? Same goes with the this one, right? Because they have very thinner enclosure, lighter enclosure. There's nothing. That's why they swell also. So there is nothing called. Okay, if you go in detail of battery chemistry, you understand there is a pressure requirement also on the cells so that they can operate at a maximum efficiency. Cell pressure requirement. What happens in case of pouch cell? That pressure is not given by this any external enclosure. In case of prismatic and cylindrical cell, they get that constant pressure. So while the charging and discharging happens, the cell are under constant pressure so that they can perform optimally. From cost perspective, if you see, from the battery cost perspective, even though they are less expensive, the manufacturing cost becomes higher because you have to attach the cell parts, you have to add multiple components on top of cells, right? Comparatively more expensive to make it because you have to cut the slots and everything. Cylindrical cell are the most cheapest cell to make because of their cylindrical jelly roll nature. You have to put a jelly roll inside a tin can, close it, that's it. There are other components, mechanical components on top of it. Safety perspective also, the cylindrical cell most safe in terms of this one because a small amount of lithium is available. They are properly enclosed. There are less chances of puncture compared to other cell form structure. Mechanical point of view also they're much more stable, right? Cycle life perspective, pouch cell has a least cycle life because they're prone to swelling. I already told there is no mechanical structure who can give the uniform pressure to it, right? There is no mechanical integrity. Packaging perspective, because of a cylindrical nature, we'll talk about the packing density also in subsequent slide. Cylindrical cell are least uh, packaging efficient. Prismatic and pouch cell are very good packaging efficient because you can stack them together, right? You can stack prismatic cell and pouch cell on top of each other. Then from thermal perspective also pouch cell are very good because directly you are cooling the cell, right? There is no enclosure, so you can directly cool. The heat transfer coefficient is very good for the pouch cell. Okay for cylindrical and prismatic cell. Future capability all have different form factor. Many people are using many cells. We'll talk about it also, which who is using what cell also. Growth trends perspective. Now you have seen that cylindrical cell, prismatic cell, pouch cell. The most prominent cell which is taking pace up now in the market is your blade batteries. Have you heard about the blade batteries? In the chat, yes or no? You know about the blade batteries? Yes, BYD, yes. Put your answers, yes, no, no, yes. Everyone is aware of that. Cattle, good. What else? S-Volt, Cattle, BYD. Have you heard about this latest innovation also by the Geely? Have you seen in the news? Yes, no. Geely also launched their recent cells, right? With 192 watt per kg. Latest innovation by the Geely, very latest in the market, right? So that is also there, right? BYD, Geely, yes, okay, right? So people are launching their different form factor, and now industry, especially the four-wheeler, is migrating towards majority of this cylinder, prismatic cell, sorry, the blade batteries only. Everyone, every auto show, if you see, people are launching their blade batteries because they have higher energy density, right? That's the best advantage with them. And there are some other cooling advantages and heat transfer advantages, mechanical packaging advantages, handling advantages, logistic advantages, multiple advantages are there. That's why the companies are moving towards the blade batteries. Chemistry, mostly it's LFP chemistry, and MC is also available. So if you see, if you zoom in out, this is mentioned as LFP. Can you see that over here? Right? Generally, mostly it's available in LFP. I'll talk about chemistry also. Don't worry, you will learn something new in the chemistry space as well, right? As we move along. Okay, let's move further. So you might be intriguing also which of the factors are being used by which companies. If you see this from this uh, image itself is very much clear. Cylindrical cell are being used only by three major suppliers, major companies: Tesla, GM, and BMW. But all of them are using prismatic cells, be it BYD, Ford, Geely, GM, Honda, sorry, not Honda, Mercedes, Renault Nissan, SAIC, Stellantis. Tesla also, they have shifted to the prismatic cell in China, if you are not aware, because they have collaborated with BYDs. Toyota, right? Prismatic cells, blade batteries are considered under prismatic form factor only, if just for a reference. Okay. So all of these people are using prismatic. Interesting. Did you know this fact? People think cylindrical, but from four-wheeler perspective, can you see this? All of them are using prismatic. And the reason is, again, the packaging efficiency of the cell, the heat transfer efficiency of the cell, cost, energy density, and all those things. Right? We'll talk about chemistry as well. Cylindrical cell, by definition itself, the packing efficiency cannot go beyond 90%, right? But prismatic cell and pouch cell, you can have very strong packing efficiency. You can stack one on top of each other. That's the benefit of your prismatic or pouch cells, right? Which is a huge benefit if you ask me, right? Because you can control it very effectively, the heat transfer and the your because you have a limited space constraint on your four wheeler. You want this to be properly packed so that you can optimize and increase your cabin volume. Okay, let's see market share by form factor. Do you can would like to answer this question? What do you think now? Which form factor has the highest market share? Please post on the chat. What do you think? Which form factor has the highest market share based on this learning? Right? So if you see the market share, exact number, if I tell you, right? Yeah, go ahead. So if you see the exact number in the market share perspective, 14% is coming from your cylindrical cell. Okay. 20% is coming from your pouch cell, and a whooping 65% come from your prismatic cells. Okay. right? Which battery Tata uses? Tata Nexon use LFP cylindrical cells. Okay, we'll show you that cell also. Don't worry. In today's session, at the end of the day, we will select one category of vehicle. We'll do complete end-to-end simulation for different chemistry, different form factors. You'll see at the end. So stay tuned till the end. Okay. Most widely used chemistry, right? This is again question. So we had to cover the form factor aspect of it. Let's see the chemistry aspect of it. So have you heard about NMC, right? So you know that NMC chemistries are known better for their specific energy. They have very high specific energy, right? What other chemistry you know? Can you put on the chat? What different chemistries you know apart from NMC? LFP, LTO, okay, and LMFP, okay, LFP, LCO, LTO, NMO, LMFP, okay. What else? Yes, yes. NMC has 311, 811. Sodium ion, very nice. LMFP, sodium air, NCA, good. Finally, someone said NCA in that direct message. Okay. So we have NCA also, right? So don't miss out this NCA. This is also very strong chemistry. Very less people talked about it. Then we have LFP as well. Now there is a pros and cons of all of them, right? NCA has very strong specific energy. Cost wise, they're most expensive as compared to in these three, right? And safety perspective also, the chances of thermal runaway is comparatively higher, right? LFP on the other hand has the big highest lifespan on all of these. This one I'm not comparing LTO because these are cathode materials. Again, if you don't know, LTO is an anode material, it's not a cathode material, but chemistry perspective it can combine with NMC. Okay, so NMC and LTO can go in combination if you don't know that. And today morning the learners from our battery BMS bootcamp, they learned today only. They also did not know that, right? So they have learned and they were surprised by that fact. Any which ways, coming back to this, so safety perspectives, the most safe batteries out of all these three batteries, specific power also is quite good, right? But from the energy density point of view, they lag a lot. That means if you're making a battery out of LFP battery pack, that will way much higher than your NNC or NCSL. And you will see in reality today, end of the day, how these numbers are changing. Okay. Let me give you a good comparison which I found out, and I think it's interesting to show you. There are multiple comparisons like this. So there are multiple chemistry, right? LFP, NMC, LCO, LTO, NCA, which you have seen in the market, right? Let's see one by one. So if you see energy density point of view, they are the least, right? We saw that this, we're just putting numbers to the graph what we saw earlier. And NCA has the highest energy density, right? From the cycle life perspective, let me use my pointer, why not? From the cycle life perspective, if you see LTO has a highest cycle life, but the least amount of energy density, right? So balance. Now, from the three-wheeler perspective, definitely I'm not bothered about the weight of the vehicle, right? But I'm bothered about my TCO. So for the best choice of battery is my LTO, right? From that perspective, what do you think? No, there are multiple slides of the day. You will see multiple interesting insights, Aditya. Okay. From charge discharge perspective, they can charge at very high rate, extremely high rate. You can charge the batteries of LTO. Okay. Right. If you compare now the cycle life of LCO or maybe compare the LFP, they're also quite good. LFP, that's why it's good chemistry. But if you see NMC and NCA, they're not so strong. This is okay. Generally, you get around 800 to 1000 cycles. But LFP and LTO offer very good amount of your cycle life. Okay. Thermal stability point of view, very important, very hot topic in the market. Your LFP and LTO gives you most stable batteries in terms of thermal, right? LCO and NMC are not good chemistries, correct? Last thing is, and if you see cycle life is already mentioned, cost perspective, we'll see in much more detail. So cost is very expensive. So now you saw from the three-wheeler perspective, the LTO is very good, right? from the cycle perspective and your life perspective, thermal stability, but cost is also high. But my three-wheeler people are decided by the cost itself also, right? So very dicey situation over here. So even if you want to use, because the cycle life is much more, the charging can be much more faster, but you have to pay a price for it. Why can't I not use LFP in that sense? Because which is giving best of everything, right? What do you think about this? LFP chemistry, now they're capable. See, okay, there is something called power cell and energy cell that depends again on that. How well you have designed your cell. You can design up to 4C, but your energy density will change correspondingly. That's why if you see there's a range given to it. Okay. Now, if you see most of the three-wheelers in the market, that's why they're using LFP battery packs. Okay. Yeah, this is not 100% true. Amrita, you rightly pointed out, right? This is not 100% true. Okay, this is actually medium. This is not high, this is medium only. There is a typo over here. You rightly pointed out. Okay, which we already saw in the last slide also, right? If you see the safety perspective, NCA was not so strong. So which is not right actually. This is a typo error over here. Rightly pointed out. Very nice. Okay. Now, if you see from energy density perspective, this is very strong. So these are the two contenders if I have to make a light vehicle. For light vehicle perspective, my LFP and LTO cannot be used. Okay. Now we'll see the simulations and everything today. We'll see how this is numbers are changing. Now from the chemistry perspective, oh, I have shown you. Sorry, I should have not shown the slide itself. So I would like to ask you, what do you think is the chemistry is the best chemistry on the market share perspective? Is it LFP, NMCA, or NCA? Which chemistry is being used? So Manohar, it seems you have seen the slide, but it's okay. I would like to see from other people also. Okay. So what chemistry do you think is from the market share perspective is the highest currently? Okay, NMC. The answer is actually not LFP, is NMC. Okay, so if you see the NCA or NMC has the highest market share as of now. Okay, in the market, not LFP cells. Okay, currently 66% of your market share is by an NCA and CM chemistry. Okay, not by LFP. Right? You might be thinking, how? Like, it's okay, but now if you see the trend perspective, right? So if you see this, okay, I should have shown the other part of it. So currently, this is my NCA or NCX, and this is your LFP cells. If you see the market share perspective, right? Is this study to the Indian market or the whole world? This is for the whole world. Okay, this is for the whole world. Right now, if you see this trend is changing, if you see next 10 years trend, if you see whatever very strong chemistry, so all this blue color curve, if you see this from here to here, this is NC, NMC, NCA, and all those things, right? Even including yellow, if I include this, that's become by NCX, right? So around 70% market share is by NCX. Let me use my pen over here, I think that will be better. So this is my NCX, so around 70% market share, right, which I saw 66% to be exactly, is NCX only 27% was there. If you see the current scenario also, this number has increased, right? So this becomes around 60 to 40%. 60% is my NCX and remaining 41% is my LFP. But if you see the growth trend, what is happening? What is happening? My LFP percentages keep on growing. And now there is a new chemistry also in the market, which is called LMFP. It also comes under that, right? So combined LMFP and LFP is changing the trend, right? So this is becoming reverse approximately next 10 years, right? So around 60% projection is there. This will be LFP, LMFP and LFP combined, and remaining only very small portion of it, which is around 30%, will be coming from NMC or NCX, I would say. Are you okay with this? Do you understand this? Did you find something insightful in this? I'll add one more insight on top of it. If you're enjoying the session, if you're enjoying the session, just put on the chat box, yes, you're enjoying the session. You're learning something new today. We'll talk about hydrogen fuel cell. So today topic is cell chemistry. So hydrogen fuel cell will not be covered under this for sure. Right? Now, interestingly, let's see other trend also, which in the market are there. Okay. Can you see the sodium ion and LMFP? These are the new chemistries. You see this, they're almost invisible over here. But can you see their projections? They're also growing. So if you see this is LMFP. So that means there is a huge strong push toward LMFP also, which will be taking care in the market. And then you have a sodium ion, which is taking place. And trust me, the projection for sodium ion and LMFP will outpass this because of their inherent nature. Okay. And sodium ion, we have covered in today's simulations also. We have considered one sodium ion cell for simulations also. So we have covered LFP cell, we have covered NMC cell, we have covered sodium ion cell for the simulation perspective. You will see the simulation results as well. You will see the voltage graphs and everything today. Okay, and the end of the session. So stay tuned. Interesting insights you will get it, because when you will compare these three cells, you will understand what's the differences between these three cells in terms of weight, performance, and everything. Okay. So now let's consider, actually the slide came directly, right? Let's consider a use case example. It's great learning. School learn with the group about hydrogen fuel cell. Okay. Now, if you see, interestingly, okay, so there is a mistake. This is not an NCA. I actually thought of using NCA. Then I thought, let me use an MC cell because data was available much more better. So what I have used in a use case, what we did is, uh, we had talked about different segment. We thought let's choose a segment to start with and compare these all cells. Let's compare different form factors. Let's compare different cell chemistries. Do you find this exciting? You would like to see the results? How we can compare the different cells for a given performance choice for a vehicle when you are choosing this? Are you looking forward to learn this? Or see the results if I'm comparing all the three things together, how they will come up, right? Do you find this interesting? Right? Great. Now let's see the cell comparison perspective, right? So, okay. So if you see the NMC cell, right, you might be aware the NMC cell has this kind of voltage curve, right, which is quite steep in nature, correct? So morning people who have attended my class, they'll be able to relate much more because they have seen the half cell, full cell, and cathode material, active material. So learners from the existing batch, they are there. So can you relate this? Maybe I'll ask after I show the slide to them. Okay, they have much more deeper understanding on this subject. Then you have LFP cells, which has much more flatter curve, but the average nominal voltage is 3.2, right? So generally, if you see, this is 3.2 nominal voltage. This is 3.65 nominal voltage. Then you have sodium ion cell, very steep curve. It starts similar to NMC, but drops much more below, right? The nominal voltage for this cell is somewhere around 3 or 2. I'll show you in the next slide, right? So I think 3 volt is a nominal voltage for this cell, but very extremely steep. So learners from the today's morning session, can you connect with this? We discussed in the morning, right? In our cell fundamental class. Can you understand this? How we arrive these numbers? They know it very well, right? Great. Okay, Devan. Okay, Sumrajan. Right. So now, because the learners from existing batch is also there, because our batch people also joined for this webinar. Okay. Now, if you see this is very different thing, right? So LFP, if you see the fundamental nature of the curve, it's much more flat, right? And if you see NMC is drooping curve, and but sodium ion, if you see the curve, it's very steep, extremely steep. So the cell performance, what you get, so is almost half, right? Starting with 4 voltage, dropping down as low as 2.2 or 2.3. So your performance will change drastically. with a sodium ion cell. So in the beginning, for suppose for a same, so power is voltage into current, correct? For keeping the same power from sodium ion cell, you have to increase your current by twice. Or if you're not increasing by current, if you're limited by the C rate, your power will drop by half. Correct? We'll show in subsequent simulations as well, right? So what we did is, generally a typical data sheet look like this, right? If you know about data sheet, so you have nominal capacity of the cell, internal resistance of the cell, dimension of the cell, weight of the cell, shell type, right? Nominal voltage, what is the watt hour of the cell, then charge and maximum charging current, 1C rating is there, maximum discharge rating, 2C which are defined for this cell, right? You get a charging time, so and so forth, right? So these are the cell data sheet which you get the information. So what I did is, for the comparison perspective, we compared four cells over here. One is back 21700 cylindrical cell, Gaussian LFP cylindrical cell, Cattle CA60 prismatic cell, and one sodium ion cell, right? So we had a C rating for different cells, right, during the charge as well as discharge, correct? So if you see the sodium ion, very high discharge rate is offering over here. Similarly to my discharge rate for this is also very high. Charge rate perspective is also quite good, right? So understand this perspective, and I think learners from today morning, they know the reason why this is less, right? Why this discharge value is less, because today morning only they covered in the session, right? Why this values are less for the sodium ion, or sorry, why this is higher for the LFP, uh, sorry, NMC cells as compared to LFP cells or other cells, right? But the charging perspective is not the same, right? Sodium ion, if you see, is very high, you can do the charging at high charge rate. LFP also goes up to 2C. Data sheet sometimes does not mention properly, right? Let's go into more detail now. So we have taken the dimension of the cell, right? These are the dimension of the cell, what is their weight and all those things, right? For prismatic, you have width and thickness as well, right? After doing some calculation, analytical calculation, you arrive on this number, okay? That for making this battery pack, right? My total cell weight, dry cell weight is 11 kgs. For my Gaussian LFP cell is 17 kgs. For cattle, a prismatic cell is 29 kgs and sodium ion is 26.4 kgs. Okay. From the pack perspective, because since the dry weight is also increasing, the enclosure weight will increase, the mounting weights will also increase. The total weight becomes 27 kgs, 41 kgs, 40 kgs, and 40.6 kgs. Right now, when if you are trying to use a sodium ion cylindrical cell as compared to your NMC cell, your vehicle weight is going to increase by 20 kgs. Right? Even if you're trying to use a prismatic cell, I'll show you much more detail. I'll show the complete layout of all those things. Do you want to see how they look when they're packaged in 3D dimension? Want to see that? Want to see if I'm packaging, if I just shown the number to you, want to see visually how they look when they are packaged in three-dimensional environment? Want to see that? Right? Like to see this? If I'm getting 10 years only, then I'll put it. Then only I'll show you. Okay, let me show the battery voltage first, okay? Because I show the cell voltage. But now if you see this, interestingly, since my NMC voltage is higher, I need lesser number of series cells to keep it as compared to my these cells, right? This is 15 actually. So if you see, I need 16 series cells for LFP because my nominal voltage, if you see, or the max voltage also if you see is lesser than my NMC cell, right? That's why I need higher. So at the battery pack level voltage, now even though when we saw that, even though my voltage difference between NMC single cell was quite high, at pack level I can compensate for this by using higher number of series cell. Okay. So if you see this, my NMC curve like this as a back battery voltage level because my 14 cells are in series for NMC, right? From LFP perspective, you see a less difference now. Do you see that as compared to the older graph? Now my LFP, because this is 16 cells in series, so the gap reduced, right, between the overall pack level voltage. So even though my pack voltage into current for cell level was very different, but pack level I could mitigate the difference by adding more cells in series. Initially, obviously, there's some difference in the initial period of SOC, but my most of my working range, I'm getting more or less same voltage. Did you know that? This is something new, right? You always think that my LFP pack voltage is very less, so my voltage also will come down very well, very less. But since you can put more number of cells in series, right? You can have more or more better performance on both the sides. What about sodium? Any guesses? So this is 14 volt systems on the Raj. We are talking about 60 volt system. So nominal is, in this case, if you see, is way beyond 50, right? So if you see the nominal voltage we saw in the previous table also, right? So if you see nominal voltage, what we have derived is 51.2, right? So one more cell across everywhere. Okay, it's not 48. So this is 51.2 nominal voltage. Okay, because the currents will come down, right? Do you want to see the sodium ion cell at pack level? Any guesses? To see this, my pack level voltage starts at 60 volt, right? At 100% CC. But can you see where it drops? Let me see the working range itself. So even my working of 10% cutoff, because this is my cutoff range, right? Because this is my DOD range. Let's say I'm operating my cell between 10 to 90%. This is way less, 38 volts, extremely less. Now imagine a vehicle operating at 50 volt and operating at 38 volt. If I'm limited by the current output, the performance will drop or not. What do you think? Right? Now, this is something a no-go situation for me if I'm making a two-wheeler, right? Let's see from the packaging perspective. Okay. You want to see visually how they look? Yeah, but you cannot have a converter, right? Because if you're putting a converter, you have to convert voltage into current, right? To whether current will go up, right? Discharge current will go up, right? So if you have to withdraw the same power, right, to keep the same power, oh, sorry, to have the same power, if you have to keep the same power, if the voltage is dropping, you have to increase your current. But you're limited by the C rates of the cell as well, right? So you cannot infinitely reduce that. There's a limitation over there as well. Okay. Now let's see first visually how the cells are getting packed. This is visual information. I'll show you the simulation results also. So what my initial constraint was, my initial constraint was I have to package my 500 by 400 by 150, right? This is my initial constraint was. Let me see what my initial targets was. I have to package within this volume, right? 500 by 400 by 150. This is my volume which I've decided. So this is my 500, right? Dimension, this is my 150. And the breadth of this is 400. Under this space, I have to package my battery. This was my target of the project. Okay. Now, if you see this, I have to package this, right? See the simulation results. So we had made the simulations for all of this. So if you see this beautifully, if I do a simulation for NMC cells, whatever we showed you, we can beautifully package. So this is around only the cell. I'm not considering the enclosure as of now. Okay, I'll show you. So this is 18650, sorry, 21700 cells, right? So this is somewhere around 70, right? 70 centimeter. That means 0.07, right? Which is mentioned over here. If you see this, this is way within 300, right? Meeting my criteria of volume, way within 350, meeting my criteria. So this cell has a volume of what? Around somewhere around 320 by around 270 or 280 by 80. Correct? As compared to my target of 500 by 400 by 150. I can easily pack this cell. Correct? What's my weight of this? If you see after this is simulation output which I'm showing, this is not manual. The earlier table which I showed was manual calculation. This is actual simulation results now. Okay. Now if you see the cell energy, my target was to get around 3.3 kilowatt hour, but somehow I'm getting 3.06 kilowatt hour, right? Which is okay for me. Now to make, after making the enclosure and all those things, my pack weight and volume comes around 90 kgs, around 20 kg of weight will come from this pack. Okay, I can pack my complete pack for this, and my pack weight is also meeting, my volume target is also meeting. Do you want to see for LFP cylindrical cell? You want to put it, you want to see for cylindrical cell how they look? How does simulation look for an LFP cylindrical cell? Put in the chat yes. I want feedback from you people. Otherwise, I'll not show you. I'll stop the session. I need this one, right? Okay. Let's see for Gaussian LFP cells. LFP cells of Gaussian, like generally, not exact dimension of this cell is being used by Tata, but Tata Nexon also uses Gaussian LFP cells only. If you don't know, right? Now, if you see, if I package my LFP cells, how they look, right? So vertically have only place. You can place them horizontally also, right? So if I package them, see dimension over here 150, no problem at all, right? Way within my range. 150 here, border case. And if you see this, this is my 550 lengthwise, right? So if I see this, this has become 550 into 150 and 150. Okay. Can I package these cells in my vehicle? Although I have more space now here, right? What I can do is I can put them in inclined case or some other arrangement and all, but quite difficult, but still possible because you can rearrange those cells, but still they are touching my boundary condition, right? This was my boundary condition. And when you design the enclosure, PCB, potting material, cell holder, and all those will become extremely difficult for package it. But still, it's not possible because you can. The benefit of cylindrical cell it you can package in any direction. There can be multiple packaging layout for this because I think still this is within the volume requirement of mine, right? If you see the pack weight in totality, that is around 27.5 kg pack weight. For the NMC cell, it was 19.5 kg approximately. So 8 kg increased here. Okay. And this is my pack volume. But if you see the energy, I'm on the same energy side which I was requiring, right? 3.07 kilowatt hour. You want to see for prismatic cells? Let me show the prismatic cell also. So when I'm placing all my prismatic cell, they will look like this. Okay. Now see this from this diagram. This is my height of the prismatic cell, again width, and this is my length. So if you see this closely, somewhere around 500 by width is somewhere around 150, okay, by somewhere around 230. This is my height, and my target was 500 into 400 into 150. So I'm crossing two criteria now. I'm not meeting my length criteria also because this is just cell. If I package the enclosure, PCB, and everything together, this will definitely increase, right? So if you see this, I'm I cannot package this and see the weight of this now, right? NMC where it was 19 kg, LFP cylindrical was 27 kg. My LFP prismatic is 41 kg. My weight is increased by 20 kg. Of my 120 kg vehicle, if I'm adding 20 kg extra, this is blunder, disastrous for me, right? Although the energy remains same, 3.07 kg. Clear? What about sodium ion cells? Let's see the sodium ion cells. Okay. Now, if you use sodium ion cells, if you package them also, right? The numbers, the pack weight perspective, they are more or less same, like sodium prismatic. Volume perspective, they come down, right? So what is the volume from this perspective? They are reaching up to around 330 within my limit, right? Somewhere around 140 in the height and around 150. Oh, okay. From the 150, right, from the length perspective, and somewhere around 150 or 140 from the height perspective, right? Is still within my limit, touching my border lines from the height perspective, but I can rearrange them and I can meet the requirement, right? But weight perspective, a no-go situation at all. From voltage perspective, no-go situation at all, right? While arranging the cell, I got 3.2 kilowatt hour battery pack. Are you getting this? Are you learning something new? Is it something new you're learning today? I want something interaction. I need some yes, no. Is it interesting? Type yes if you're something learning something new. Is it interesting for you? Great. Now, if you see this, now we have talked about the package. We have talked about the overall volume, weight, right? What about the price? Have to see the price also, right? Because when you're deciding a cell, the cost also matters a lot. Okay. So if you see this, the projection in 2014, why I'm showing you old result also, projection was in 2024, you will be somewhere around less than $100. Okay. And somewhere around 2027, you will reach $50 roadmap of cell lithium ion battery. If you see the latest figure, we have already reached this $50 benchmark for FP cell in China. Although the same prices may not be available in India, that might be around 60 to $65 rupees. But this has, we have already reached that level of prices which was supposed to happen, right? If you see now, if you're choosing an MC cell, right, $50 becomes, so you have to pay somewhere around 20% penalty or 30% penalty on top of it, right? So if you see the NMC cells are 30% expensive, right? Approximately. Now, this is China prices, latest prices, right? And if you're using high nickel like an MC811, right? The prices are much more higher, around 60% higher, right? So this is 60% higher than LFP. So there are always pros and cons of using the things. So if you want to meet your vehicle performance, you don't want to increase the weight. So how much weight you are increasing? Let me show you, right? I'll show in the next slide. So if you see the manufacturers also, again, cattle, since they work on LFP and they work on your prismatic cells, they are the biggest supplier out there. Okay. Then you have LG Chem Solution, BYD, they're all catching up. This is latest data. Everything is latest data. Okay. From the, now if I compare all these cells which you saw, right? Let me put a comparison over here. So from the water per liter perspective, right? From the water per liter perspective, right? Which is the packaging requirement, right? I got highest specific energy from the NMC cells, right? Bag cell gave me highest volumetric efficiency, and prismatic cell gave me worst packaging efficiency. Sodium also was better than LFP cell if you see this from volumetric perspective. Correct? Do you agree with this? Aligned? You saw the numbers of the box volume by yourself, right? Yes, no, right? You saw by yourself these numbers when we saw the box volume over there. Okay. Let's see the next number of water per kg. What we saw, even though it was providing me very high volumetric efficiency, it was giving worst water per kg. That means it was the most heavy cell. Okay. So Although it's giving me good volumetric efficiency as compared to LFP cylindrical cell, but if you see, it is the most heavy cell, right? Lowest water per kg, right? If you see, compare your an MC cell, Gaussian cylindrical cell, prismatic cell for cattle, right? This is the lowest one, right? And if you see the battery volume when we made, the volume what we made was highest for the your this one, right? So cattle prismatic was consuming huge amount of space. It's related to with this only, same thing, right? And my NMC cell was considering very less space. NMC also was okay for me, right? So if you see from volume perspective, I can put my sodium ion battery in my vehicle, right? But my performance will degrade like anything. So if my 19.7 kg was there, and correspondingly I was putting 45 kg of sodium ion battery. And from perspond perspective also you saw that it was flat, but sodium ion was dropping like this. So the sodium ion battery is not suitable for you from performance perspective as well as from weight perspective in your two-wheeler. So do you think that sodium ion will come in the future for two-wheeler? What do you think? In put in the chat box. Can you use sodium ion batteries in your two-wheelers from weight and performance perspective? Yes, no, or people have slept already? No. Are you not? No reality, no really as of now. Okay. I want to keep it awake only. Okay. Right? We can also simulate now, since we already did the simulation of all these battery packs. I thought of showing you the simulations also, what is the impact on performance on real time, but somehow we were out of time. So we thought, okay, we'll keep it reserved for next webinar, right? So the simulation part of it, how this, yeah, they have launched, but you should understand this, right? They can launch it for the three-wheeler, is still acceptable, but it cannot be acceptable in two-wheeler. For three-wheeler, yes, there is no issue using them on three-wheeler. Please understand. Again, the sodium ion battery, what they have made, they will use in the three-wheeler because performance is not an issue, space is not an issue, right? Weight is not an issue. So from storage application point of view, energy storage point of view, and as well as your three-wheeler perspective, low speed three-wheeler, definitely sodium ion will go, but not definitely from performance vehicle point of view, because performance degradation is very high. Yeah. Now we will show the simulation also. We actually took around 4 or 5 days to make this much itself, making the simulations and all. We thought, okay, let's simulation part of it, system sizing part of it will cover in next class, right? Because of we already late now. Let me give you a brief about Techlanz also as my responsibility, right? So what Techlanz is? Techlanz is global community of EV ecosystem. We provide training programs. We provide industry hardware along with the training programs. We provide engineering services also. Okay, so if you have engineering services requirement, you can reach out to us. We also conduct this kind of webinars to just share our knowledge with the people. We have open source EV community. If you are not joined, please join. You can openly interact with people and ask your questions there. Okay. We are a startup in a registered startup in India, startup India certified company. Okay. We are founded, me and Lokesh are the co-founder of this company. We both are IIT Delhi and IIT Kharagpur alumni. We work with Mahindra, Tata, Mahindra, Simple Energy. He we worked with Mercedes, Ather, right? Filed multiple patents and paper, core technical people, right? And we also have some programs which are running in the market. If you want to listen to it, you can listen. I don't want to spam other people. If you want to understand what programs, training programs we are offering, you can stay and listen to it. If you want to drop off, you are free to drop off. I don't want to spam people because knowledge sharing, I have done it. If you want to understand how deep we go in the simulations as well, what simulation tools we use, you will understand from this, right? So we have Battery Plus BMS Bootcamp, which is already running right now. Uh, Learners from the existing batch is also there. We go deep dive in MATLAB Simulink module. We make you expert in that first. Then we go in cell module. making you understand what different cell fundamentals, cell testing, cell modeling, battery hardware design, BMS hardware design, the PCB design, circuit simulation, schematic design, everything we teach you in this BMS bootcamp. Then we also do the algorithm design based on this, right? Then we also take care of the firmware design aspect of this, the embedded C programming, communication protocol, everything will teach you in this program. Apart from that, we do the battery pack design also. And I already showed the battery pack design, right? That was very tip of the iceberg, because when we do the battery pack designing, when we train people, we train people from the mechanical aspect of it, electrical aspect of it, thermal aspect of it, battery pack construction aspects of it, and homologation perspective of this, right? We also cover different projects, so every module is project driven. So we decide, okay, in this module we have to make this, and then we make that particular thing in that particular module. Already one batch is running on the June, second batch is starting on August. We use different tools also, because skill set is very important. We believe in theoretical knowledge will not help you grow in your career. You should have the hardcore skills with making your hands dirty to get a right placement and grow in your career. So we cover multiple tool sets. Someone asked me, do you cover the physics-based modeling? Yes, we cover the physics-based modeling, right? So we cover COMSOL analysis also. Okay. Apart, and we also give you real hardware, right? Important thing is we have developed this custom hardware. We believe you have to make your hands dirty to learn the things practically. So we have developed the custom hardware which you dispatch to your home, and which you can do the practice by your own self. You will be testing it out, right? One second. I have to show the Techlanz logo, which comes when, right? So this is our own custom hardware which we have developed, right? You will learn how to develop the algorithms in the MBD system, how to code the algorithms on the firmware, then how to integrate the MBD on the hardware, and you will be able to simulate different performances, different, if you see the voltages, Coulomb counting, Kalman filtering, how the over voltage protection is happening, under voltage protection is happening, all the algorithms you'll be able to train. And that's the real joy of learning. You'll be able to change the different load resistance on this, and you will see and how you are able to do it. Now, one thing important is, since we are doing live classes, every week we have live classes. It's an interactive session like we are having today, right? You can unmute and speak. Every week we have live sessions, and we give you hardware also. The reason for giving hardware, because not everyone can join to the offline sessions and come to lab, right? But when we give you the hardware, you have very hands-on experience on the things. You can see how the lithium cells are behaving, how their charging discharging is happening, how the SOC is changing, what is the current which is going, right? Different how the temperature is changing, and you can code it by yourself, because this is development board, and this is not Arduino or Raspberry Pi. We have developed on STM microcontroller, which is industry grade microcontroller, because in industry, if you're working, you will be working on ST or Infineon or TI or NXP, right? So those level of microcontroller we have used for ourselves. Okay. And now next batch, we are starting on 1st of August. The enrollment is open. So Keshav, are you there? You can, uh, we do the consultancy. I'll come at the last. I'll allow you to speak and unmute and speak. You can ask me the questions. Let me just cover briefly this, right? So you can join the next batch if you want, which is starting on 1st of August. Existing batch is already running. We have already covered 1.5 months now in that. So next batch is open for enrollment. Okay. And the fees consists of all the hardware, all the software, everything, all the licenses we give you as a part of the package. So you don't have to bother about anything else. Okay. Second course which we have launched is system sizing masterclass. Some people who are not from the component manufacturing or from the startups, they are working in big OEMs. They generally don't design the BMS hardware, right? They have to buy from the supplier. They don't design the algorithm by themselves sometime, right? Everything comes from supplier. For them, this module is much more important, which we have recently launched. This from system sizing perspective, where you learn how to select the right component. The way I have shown you in the morning, right? How the capacity sizing happens. So if you see, we teach you from, let me open this. Okay. So we take you from the tractive force estimation, what is the road load requirement on the vehicle, then motor sizing and selection, different drive cycles, simulations, right? This is what, because I also come from the OEM background as well. So this is something what we don't know OEM. We give the targets to the suppliers, right? We have to size the components. The component is procured from outside, right? Then you the battery sizing, what is the what is the series valve combination, what is the kilowatt hour requirement, right? Battery capacity, how much is required, which type of battery cell you have to use. Let me use a pointer over here, right? So learn, estimate the battery capacity, what should the voltage of my battery pack. Then the different peripheral of LV system, my DC-DC, what should be the capacity of my DC-DC, what my LV battery capacity should be, right? So all these things we take care in the electrical system sizing. We have thermal system sizing as well, which we have launched. In that, you understand how to simulate the heat generation of battery packs, how to design the battery cooling system, right? How to estimate the load cooling requirement of that, steady state condition or transient condition as well, where you learn all these simulations. You also learn how the motor and motor cooling sizing, because you have designed the LTR for that, right? The low temperature radiator for that. Similarly, for DC-DC and charger also, you have to estimate what's my cooling requirement, what's my flow rate requirements, all these things you learn over here. And the most advanced topic is cabin cooling. There is no course available for that in the market. I think none of these are available in the market. We have integrated that as well because the cabin cooling is very prominent in four-wheel industry because the complete HVAC load decides your range of the vehicle. Okay, so how you will estimate the cooling load of the cabin, you will learn from this how to. I think there is some typo error. I would rather open the brochure, right? Let me open the brochure because there's some typo error. That is not something what we are doing it, right? So you will, whatever people who need the brochure, put on the chat box. We'll share the brochure the link with you. So then the requirement of cooling load, estimate the cooling load, which are their heat load, solar load, right? Performing the lump mass analysis simulation, do the compressor sizing, evaporator sizing, condenser sizing of that. So all this is covered under the electrical system sizing bootcamp. So we have two bootcamps, system sizing. Mein. One is the system sizing of electrical system. Second thing is thermal. Okay, so you can either opt for any one of them or you can opt for both of them, right? Both options are available, right? And Keshav, are you there in the session? Can you post the chat? You can, and okay. And if you have any doubts, you can go through our courses. Let me put this on the chat box if you're interested. So this is our battery plus BMS bootcamp, which is available, right? These are our services, what we offer, right? I'll just keep it 1 second. This is our WhatsApp community, right? You can join the WhatsApp community as well. You can brainstorm on all these things. Okay, this is my, can I copy the link? Yeah, this is our YouTube channel. You can watch all our previous webinars. And if you want to stay updated on the latest technology trends, you can follow our LinkedIn channel. We keep on posting the technology trends as well over there. Now the podium is free to ask any question. You have any question, please unmute yourself and ask.